Good morning. I'm Vanda Vicars, Executive Consultant with Global Risk Institute, and on behalf of GRI, I welcome you to Demystifying Quantum Computing, Its Potential and Threats, featuring Dr. Michele Mosca, who I will introduce in a moment. First, I want to acknowledge that GRI's offices are in Toronto, which is situated on the traditional territory of many nations and is covered by Treaty 13 with the Mississaugas of the Credit, and now home to many diverse nations, Inuit and Métis people. Because quantum computing is a developing technology and is not well understood by all, this webinar will take on a slightly different format, which I will review now along with some housekeeping notes. First, please note that this session is being recorded and will be shared on our website. We will begin the session with a brief fireside chat with Dr. Mosca, where we'll explore the nature and history of quantum computing and progress to date. Then Dr. Mosca will present findings from the latest quantum threat timeline report. We would then start the Q&A period with some prepared questions and open the floor to audience questions. Please submit your questions through the chat. We will address as many as time will allow. And a reminder, when you exit the webinar, you'll be prompted to fill in our event survey. Your feedback will help us continue to deliver high quality programming, so please take a few moments to complete that survey. So let's start. Quantum computing technology has been in development since the early 80s, when it became apparent that the laws of quantum mechanics would be needed to solve problems that classical computers could not deal with. It gives me great pleasure to introduce Dr. Michele Mosca. Michele is the leading global expert at the intersection of quantum computing and cybersecurity. And he is also a founder of the world-leading Institute for Quantum Computing, a professor at the Department of Combinatorics and Optimization at the University of Waterloo, and a founding member of the Perimeter Institute of Theoretical Physics. He holds a Bachelor of Mathematics from the University of Waterloo, a Master of Science and Doctorate in Quantum Computer Algorithms from Oxford. He was appointed as a Knight of the Order of Merit by the Government of Italy in 2018, recognizing his contributions in quantum information science and digital security. His work on quantum computing has been published widely in top journals and textbooks, and he is also CEO and co-founder of EvolutionQ, a provider of quantum computing security solutions. Michele, welcome. Please share with our audience, what is quantum computing technology and what distinguishes it from the computers we use every day?
Yeah. Hello, Vanda. Great to be here with you and GRI, all your guests and friends. Over a century ago, physicists were struggling to explain some macroscopically observable phenomena and with the laws of physics at the time, and they couldn't do it without actually tweaking the laws of physics. So beneath the laws of physics we were used to seeing, there are some other laws, the quantum laws, and if you turn the knobs, if the knobs are set a certain way, you can suddenly explain things we were seeing at the time. So we can now explain why these impossible things were happening. But over the last century, we've moved from just observing the effect of those laws to actually turning the knobs and controlling them and engineering things that should have been impossible, were impossible, including computations. And if we start harnessing, bits in a way where we can control them quantum mechanically, the resulting calculations would take an astronomical and exponential amount of regular computing power. And so now we have devices that have been commercially available and can continue to increase in power. The challenge is, what is this special kind of quantum parallelism useful for? So it's not good at everything. So for certain problems, it's astronomically, exponentially more powerful. For others, it's substantially more powerful. And for a broad range of problems, it's not more helpful at all. So you wouldn't use it, just like you wouldn't use an airplane, to go to the corner store to buy milk. You would only use quantum computing power for very specialized and important tasks.
So many of the key technology players in the space have developed their own roadmaps towards achieving quantum supremacy. Google achieved a couple of its milestones in December of 2024 and announced the Willow processor. Can you tell us why this achievement, what this achievement is, and what it means to the race of developing a stable quantum device?
When we first, started 30 plus years ago, when more and more scientists started looking into quantum computing, the kinds of computers we could build at the time were so noisy that before, errors quickly overtook the computation. And the sizes of computations you could implement on a quantum computer, you could simulate on a laptop, if not by hand. So that's like 20, 30 years ago. About a decade, but over time, the error rates kept going down and down. So you could do bigger and bigger quantum computations. With that exponential overhead to simulate it on a regular computer, about a decade ago, Google and then others just demonstrated proof of concept calculations where you couldn't possibly do it, or it would take astronomically more classical regular computing power to solve the same problem as a quantum computer. So a decade ago, we already, just by reducing the noise, we're able to do big enough, noisy, but big enough quantum computations to outperform regular computers. Were they useful? Well, we're still trying to leverage these noisy intermediate scale quantum devices. But ultimately, if you want to do a bigger and bigger computer, you can't build a less and less noisy computer every time. So, and that's true with classical computers too. The way we get around it classically is using error correction. We introduce a bit of redundancy into the calculation so it can handle a few errors. You detect them and you correct them. And we knew the theory of quantum error correction since the 90s. And we've been on this long journey of implementing all the building blocks and integrating them. Because in theory, we knew we can deal with error rates and do arbitrarily large computers if only we do enough error correction. And it was a great theory. And just in the last few quarters, we started demonstrating, by we, I mean, the companies like Google and IBM and QEra and others, and in academic labs, that this theory works. We can actually reduce the error rates so we can ultimately, as we scale up these devices, do arbitrarily large quantum computations. Just like today, we can do bigger and bigger classical computations. We just have to build bigger devices and correct the errors. So it was one of the most important milestones, probably the most important milestone to date, sort of validating that we can correct for quantum errors and build as big a quantum computer as we'd like.
So let's just make sure the audience understand what you mean by noisy, because noisy isn't just noise. It's like, that's the errors, right? Like, let's make sure they all understand it from your point of view.
It's all the imperfections in the devices. Like you prepare something in a 0, there's a small chance it'll flip into a 1, or you're supposed to rotate it 30 degrees, but maybe you rotate it 31 degrees. All those sorts, and then you might have stray particles come and dislodge your bits. So there's an array of different types of imperfections that can impact the device. We can't engineer for perfection, right? We engineer for something pretty good, and then architect to be able to detect and correct those errors that inevitably happen.
Okay, great. Thank you. So with all this power that quantum computing can bring us, there are definitely some benefits to many industries. And then, of course, there's threats. And so let's discuss the threats and let's talk about the quantum threat. And so I'm going to hand it over to you because I know over the last few years, you've been authoring on our website. We've been authoring a quantum threat timeline. And the latest installment was just posted in December, I think. And so let me hand it over to you. Now that we understand kind of fundamentally, quantum computers are very different than classical computers. They handle different kinds of problems. So now that we know the basis, let me hand it over to you to talk about the benefits, the threats.
Yeah, we're obviously super excited about the benefits, and it's just part of the safe, and sort of unencumbered taking advantage of this technology that we also mitigate its known threats and be ready to mitigate the unexpected threats. So up until the 1980s or so, when we're communicating information, most people didn't even bother to protect it, to encrypt it, to protect its integrity. It was just fine, except for governments, military, intelligence, and some financial applications. But as the internet started to evolve and become this amazingly useful business tool, suddenly we couldn't be complacent. Like there was a real threat now. Adversaries we want to trust these technologies, but we have to make them trustworthy, right? And the way to make things like the internet and wireless communications trustworthy and that adversaries aren't stealing information assets or manipulating them is through cryptography. But again, up until the 90s, the cryptography we used was very manual and out of band. You'd have to exchange cryptographic materials manually and then use those to encrypt and authenticate. But public key cryptography, which was invented in the 70s, was this magical, almost magical way to do a lot of that heavy lifting in band, right? So it really made things much more scalable. And it's hard to imagine the last 30 years of economic growth without this mathematical way of exchanging cryptographic material. So that was great. We had a problem, we came up with the mitigation, and then we pretty much grew and migrated the whole global economy, on this foundation protected by a really small set of algorithms. So it quickly, over time, not quickly, but over 3 decades or so, became, the resilience of these foundations, of these protections, need to be taken into account. And we knew that, but nobody really cared because we didn't actually know how to break them. But in theory, we said that, and the breaks we did have were somewhat gradual and we could deal with them at the time. But quantum computing, the reason we know it can be exponentially more powerful, because one problem we learned in 1994 could solve astronomically better than a regular computer is breaking those codes. Right? Again, in the 90s, it would have been bad if those codes were broken, but now there really isn't any sector of the global economy, no aspect of our lives that wouldn't directly or indirectly be impacted by these codes being broken. The confidentiality of the information, the integrity, the authenticity, and even the availability of these digital platforms would all be seriously and systemically threatened if this quantum code breaking becomes a reality before we've done something about it.
So let me hand it over to you to go through. You've got a few slides that are prepared. And then I think at the end of that, we'll be going into a Q&A discussion. So for all the participants, please use the Q&A chat if you've got any questions along the way, and we'll deal with them after Michele goes through his presentation.
Yeah, no, I'll just take a few minutes and leave time for the interesting discussion. So as we mentioned already, we're very excited about harnessing all the wealth creation capabilities, all the possibilities of solving really important problems for humanity. We know it's powerful because it's astronomically more powerful at breaking the codes underpinning today's economy. And one of the things we explored in our survey with the several dozen of the world's leading experts is, when will we have useful quantum computers? So right now, I think it's fair enough to say they're useful R&D tools, which is already saying something. But when are they going to be commercially useful? In part because that will fuel more investment in the further advancement of the technology. And these are generally folks who are pretty cautious and reserved in their estimates of things and avoid hype. But you see this growing confidence that they will be commercially useful in 3, 5, 10 years. And I would say this chart we see here is sort of the combination of two curves in a sense. One is, will these noisy, not error-corrected computers be commercially useful in 1, 3, 5 years? They're available, but obviously their breadth of applicability is smaller because there's a size limit on how big of a computation you can do with them, but we have them sooner. And the other is, as we get not just 1 to 10 of these error-corrected quantum bits that Google and others have demonstrated, when we get 50 to 100 or 200, we'll have a much, much wider range of calculations, useful calculations we can do, right? So you kind of add these two curves together implicitly, and you get these estimates by our colleagues that suggest these will already be commercially useful with substantial probability in the next 3 to 5 years, which will, of course, continue to accelerate investment and application of these devices. In terms of the bottom line, it's really helpful to be precise, because asking when will you have a quantum computer, when we have a useful quantum computer, that's too ambiguous and too vague. So we've been asking specifically, when will we have a quantum computer capable of breaking this specific code, right? And on the left is last year's estimates. And just to clarify, we would ask people, is it less than 1%, 1 to 5%, 5 to 30%? And so we average those ranges, right? And we get sort of these averaged ranges. And the 5-year range went from 4 to 11% to 5 to 14%. And the 10-year sort of risk estimate went from 17 to 31% to 19 to 34%, and so on. And it keeps nudging up based on, again, a lot of the analysis that's in the full report. So it's already, and then I generally stop elaborating because 5 to 10-year risk is already material and needs to be addressed rather urgently. And there was, we've been for many, many years trying to create understanding and give sort of non-hype insight and understanding of what the risk is, because we don't want to overestimate it, because there's a lot of other challenges we need to deal with, and we don't want to overinvest in this problem and underinvest in others, but we don't want to underestimate it, right? It's okay to be a year early. It's not okay to be a day late. So we've been trying to give reasonable, accurate estimates, and I would say there's more confusion was sowed, let's say a few weeks ago, by a comment that I think was maybe oversimplified or too maybe not sophisticated, not elaborated enough. And of course, now there's going to be, I guess, what some have called the apology tour, or maybe some more discussion of that. But statements about we're not going to have useful quantum computers for 20 years sowed a lot of confusion. We've been trying very hard to create, responsible awareness and action. And part of, because it's hard to take something that is, 2 or 3 dimensional, landscape of possibility and collapse it into one point. That's going to lead to oversimplification and maybe cause confusion. So if you look at our risk estimates, for example, if you're really worried about mitigating risk, you're worried about a 5 to 14% chance you have to act within 5 years. On the other hand, if you're looking to benefit commercially from this capability and you want to have a really high degree of confidence of an ROI over 80%, yeah, then maybe it is 20 years, right? And a whole other dimension that's also needs to be considered is, but how big of a computer are we talking about? This chart is focused on a cryptographically relevant quantum computer, which is substantially bigger than some positive applications and substantially smaller than others, right? But if you happen to have a commercial application that needs the same amount of computing power as breaking these codes, we have some good estimates here. If you need a smaller computer, well, then it'll be a few years earlier. If you need a more powerful computer, it'll be a few years later. So there's many different factors to take into account. And certainly commercial usefulness, it'll happen before we have cryptographic relevance. Like regular computers were already commercially useful in the 80s. They're more useful in the 90s. And so every decade, they become even more value creating. So we're certainly going to, I think, reach that mark before 20 years. It'll be at a substantial level within 20 years. But in terms of risk mitigation, we really need to be hyper-focused on the 5 to 10-year horizon. Why? Well, 3 factors, right? For one, some of our information has a shelf life. It needs to remain confidential and retain its integrity even, but let's even just focus on confidentiality for some number of years, right? And I would say if you're worried about the shelf, like long-term confidentiality needs, we're already really, really late in the game, but that is a factor. So, but I just want to be clear, even if you're like, I'm not so worried about confidentiality, you still have a problem, because it takes several years to migrate your platforms to be resilient to this known threat. It's not a Tuesday update. It's not a patch. It's really a re-architecting. It's one of the most audacious sort of technology migration, software migrations we've ever done. So it takes time to do properly. If you don't do it properly, you're inviting all sorts of chaos, system outage without adversaries, even more attacks enabled by adversaries without quantum computers. So you don't want to rush this migration. So you have Y years to migrate, X years you're supposed to retain confidentiality. The question is, will that quantum threat appear before or after the sum of those 2 numbers, right? So you come with your risk tolerance. You can go to our charts and pick which date that corresponds to, and you really want to make sure your migration plus the shelf time is less than that threat timeline. Right? That's what quantum risk exercises for over a decade have been studying very closely now. And what this threat timeline report does is give us as much visibility, as much insight as we can on the threat timeline part. The migration time and the shelf time, those are your, I mean, you control. The shelf time is a business or regulatory decision. The migration time is the part we control to some extent. Now, there's been a few examples where people have really accepted their responsibilities and demonstrated leadership here. A small handful of governments have said, look, gone to their vendors and said, we need quantum safe solutions. And this is generally national defense, intelligence, and other government agencies by a certain date. And you see what the US government did, for example, is they broke it up along 6 different types of technology. And for some of them, they said, we want it as an option in 2022. It must be the default in 25, and we won't accept the old stuff by 2030, right? And for others, the timeline shifted a little bit, right? So that was, I think, a very positive sign and something to be replicated, and a few other governments around the world have done that. The National Institute of Standards and Technology in the United States, so to be clear, the US government asked for this in 2015, right? So in 2015, they said, we are migrating to these quantum resistant solutions in the not too distant future, by which they meant 2030, right? So 15 years is considered sort of an aggressive timeline to do a cryptographic migration. NIST, fortunately, had been preparing for this day back before 2015 and responded and has produced, I think, a trustworthy set of algorithms to replace the current ones. A number of other organizations have stepped up because often there really isn't clear responsibility, like who's in charge of the cybersecurity of the global financial system. Nobody puts up their hand, right? But players have nonetheless demonstrated leadership and started convening different stakeholders to articulate the challenges and opportunities to work together, such as the World Economic Forum, working together with global financial regulators, the Financial Services Information Sharing and Analysis Center, and the Canadian government convenes the Canadian Forum for Digital Infrastructure Resilience. We have a Quantum Readiness Working Group. We've been convening many stakeholders and sharing best practices, going through use cases and scenarios, learning, and then sharing those best practices so others can go faster and better. We also, with the support of GRI, have done a report where we interviewed risk leaders, cyber risk leaders in the financial sector, related industries, supporting industries, and asked them a list of questions. So this is a bit of a just a heads up to, you might want to check out this report when it's released shortly. But some of the findings, I just summarized briefly here. Obviously, there's general awareness, but urgency varies. Regulation will obviously drive greater urgency. Of course, we want good regulation that helps make us more secure and resilient, and not some of the more cumbersome ones that don't work so much. So obviously, we have a chance to get ahead of this and have smart regulatory frameworks. It's really hard with cyber risk. The more nebulous and forward-looking it is, or in the future it is, the harder it is to internalize it. That's not new. Firefighting versus fire prevention, they're very different in how they're handled. But what we've noticed is those concerned with reputational risk, there seems to be a little more traction there in treating this alongside sort of reputational risk as a motivator versus the harder task of trying to really quantify this. There's also some moral hazard, I would say personally here as well, which makes it hard to take responsibility, but we're noticing some of these barriers to action. I won't go through everything here, but just just a heads up that there's some insights we've gleaned from thought leaders in industry, and one of the things that will again could accelerate quantum security solutions is the fact that there's now standardized options, right, that are being certified and so on. So it makes it a lot easier to act alongside. So on the one side, we have the threat is getting closer. Regulators are asking questions. There's motivation to act. Standards are available. Makes it easier to act. So there's a bit of a multiplier effect there we're anticipating. Another thing that helps a lot is to see that others are doing it. So there's a wide range of vendors. Of course, they've been preparing this for years. So it's not like you can suddenly me too this in 6 months, but there's been great activity. And these are honestly first steps. There's a lot more to be done by these organizations, deploying these new algorithms, also deploying the defense in depth, the alternatives, in case these algorithms are broken in the future, such as JP Morgan Chase and others. So this also helps, the fact that they're doing it and talking about it also helps increase awareness and motivate activity. Some low-hanging fruit, because some of you are saying, well, we're not one of the top 10 banks in the world. What are we supposed to do? Well, some easy sort of free activity is engaging with your vendors and but what do I ask them? Well, through Sifter, we've produced a list of questions, 8 questions you can ask your vendors, and other questions you can ask third parties. Just some guidance. You might pick one or more of them and start engaging with your vendors in just to better understand how they're handling this. How ready are they going to be to help you manage your risk? It really helps a lot because we've been talking to stakeholders all over the map, and with when you talk to the vendors, they say, well, yeah, we get it, but our customers aren't asking. When we talk to the customers and they say, yeah, but we rely on our vendors. But that dialogue is really important. One of the most important take-home messages, I would say, is we were lucky this time, right? We built this, we had a foundation fit for a 3-story building. We built this massive high-rise on it and kind of hoped for the best. A break did happen, but we were lucky that it wasn't immediate. We had 3 decades to do something. That's luck. We can't rely on luck. We shouldn't be afraid. Just prepare. Actually, this is one of the easiest, I would say, massive global problems to deal with. So I think it's all within our power to deal with it. But we just can't rely on luck going forward. We need to architect for resilience. And just to wrap up then, what does that mean? I think there needs to be a readiness scorecard. If you're going to depend on a technology such as cryptography to protect really vital assets, and not just secrets, but even the availability of those platforms, the ability to keep doing business, keep moving money around, and so on, you should know, okay, if this is broken, I know what happens. I have enough visibility. I've done my inventories. I've assessed the risk. I kind of know what the impact is. And item 2, I can express confidence that it won't be a catastrophe. It'll be bad, maybe, but it won't be a catastrophe. It's a recoverable event. We've anticipated enough. We have enough, fire prevention, fire planning that it won't destroy everything. And so there'll be a bit of an emergency situation that is survivable, and we'll be able to fix the broken things and get back to normal in a reasonable amount of time. We know how to do those things, but we have to ask for it. We have to architect for this and ask for that cryptographic diversity and agility and defense in depth. So I'll stop there. It's probably a good point to now re-engage with Vanda and everyone in the audience.
Great. Thank you very much, Michele. And I think we'll just move to our Q&A session now so we can bring the slides down. Michele, I've already started receiving many questions here, and I think one of the points that we need to explain a little bit more is what would happen. In other words, because I'm getting questions that are indicating that people, understand cyber risks, understand cyber threats today currently, but in this case, when we talk about cryptography, when we talk about, we should talk about RSA and RSA being, broken and moving to the new NIST standard. Let's explain that layer a little bit because we're getting confusion, I think, a little bit on when I prepared for Y2K, I changed all my programs. Well, that's a different layer. So maybe we'd spend a little bit of time explaining what could happen and how.
What could happen on the threat side versus
like that, just like what gets broken, how does it get broken? In other words, right
And it's,
now we didn't talk about harvesting, so maybe that's
yeah,
something, right?
that's one. So there's the iceberg, right? There's the stuff we know concretely, and a lot of it is we don't know, and we don't really want to learn the hard way how bad it could be. So we'll often hear about the harvest now, decrypt later attacks, not because they're necessarily the worst impact, but they're the earliest one you need to start planning for. Because everything you're transmitting now and in the last 5, 10 years and so on, if it's been recorded in transit, it's being hard, people are waiting. I mean, our governments have said people are recording this for future exploitation. They didn't say maybe, they said it's happening, right? Is it happening to you? Are they going to do that? We don't know, but we know it's possible. We know it's happening, that when the code breaking capabilities become available, this previously unreadable information becomes readable and exploitable in all sorts of different ways that honestly, we don't know the full extent of cybercrime in 5 to 10 years, which is powered by AI and other things, right? So we understand the vulnerability, how threat actors will exploit it in 5 to 10 years. It's really hard to put an upper bound on it. We know it's technologically possible today. There'll be even more possible tomorrow. And then we're at the mercy of, will they want to, exploit this against us and compromise our confidential information. But there's also, in the shorter term, if you don't migrate in time, then the other risk is, for example, auto updates. Like all the software, when you install, and these are all happening invisibly in the background. The reason it works is because you have digital signatures authenticating this is from the person you trust. If you could break digital signatures, you can impersonate whoever you want. And there's no distinguishing an adversary from the people you've chosen to trust. So then you lose the trust. The trustworthiness is gone, right? Because your primary mechanism of trusting software or just other entities disappears. At least one of the main mechanisms. So apart from the secrets from the past and present, until you finally switch to quantum safe algorithms, those are vulnerable. Again, the availability of these systems implicitly, like fraud becomes possible and so on, because people can access systems. Apart from getting the confidentiality, they can steal digital assets, they can change them. And implicitly, one of the things that worries me is it obviously threatens the availability of these platforms with no clear remediation date if you don't have a plan in advance. Because once the platforms are no longer trustworthy, they won't be trusted and they won't be used. And we don't in general have a game plan to work without these codes. Not to mention, if you can impersonate legitimate system administrators and people with very high access privileges, you can also, again, take control of systems and do all sorts of damage. These are things we know, but what we don't know, what we've never really tested. And Paul Kosher at the RSA conference, he's one of the pioneers of many things in cryptography, including side channel attacks, said we kind of know what happens if 1% of our systems go down in any given day, right? Some small percentage, sort of randomly, it's bad, but then there's enough of the economy, enough of our systems are working, we can detect and remediate. We don't know what happens if there's a systemic failure. So part of that, we actually don't know how bad it could be if several of our critical infrastructures are compromised without a game plan already in place.
Great. So I think that deals with a few of the questions that I'm seeing here, which is explaining what could happen. So today, I equate how information moves from point A to point B as we're all little squirrels and we love our little nuts. And we take the nut, and the hard shell of the nut is cryptography, and the inside of the nut is what we're protecting. And the only way to break the nut when you get from point A to point B is understanding the keys that allow you to break the nuts. When you get into quantum computers, the quantum computers can break the nuts by themselves because they can work so fast, and they're just a bunch of people, little squirrels breaking nuts. So I just thought of that as a little bit of an analogy to explain to people that's what the cryptography issue is. Now, you mentioned NIST. NIST published last year, I think, the quantum safe algorithms. And I think we're seeing a couple of questions here about, okay, so, are we going to be relying on the, the third parties, the cloud providers, the hardware providers? Who are we going to be relying on to move to these new standards? Are we relying on, so that's one of the questions here. Are we relying on the library developers, the vendors to have, PC capability?
So let's assume we, as a large financial institution, there's roughly 3 categories. There indeed your cloud and other service providers. There's people who provide you the apps and software you use yourselves. And then there's some stuff you built in-house, typically. And they all need to be fixed and still interoperate and fixed while you're migrating them. So it's hard to change the wheels on the bus while you're driving it. It's another reason we're saying get ahead of it, have a dress rehearsal, start doing some of the easy pieces first. But you are going to rely kind of on all of the above. But it's not going to be a simple, oh, there's going to be a new library and it'll just magically permeate through everything. Much of it will happen sort of invisibly in the background. That's great. It's that 10 to 20% that won't, that you really need to get ahead of. Like, for example, I once had somebody from one of the largest central banks in the world say, will this stuff work on smart cards? I'm like, I don't know. You should look into that, shouldn't you? Because some of it won't. In fact, a lot of it wouldn't work on a smart card. So all those niches and non-standard cases need to be looked at in a prioritized way to make sure you do actually have a solution. So you got to do that analysis, do a few dress rehearsals for the prioritized way. Some stuff's going to break, and we'll just know of it. We just want to make sure it's nothing super critical.
Okay, thank you. So as we move forward and trying to plan for this, I think some things that you've talked about, and I'm just interpreting some of the questions here, is the timeline. And one of the key things is talking about the inventory of what people have or what the institutions have. Can you elaborate a little bit on that, how you're seeing that being done? 3-part question, the inventory, how you're seeing being done, and are we doing enough?
Yeah, so one of the US government specifically, when it was starting to become more prescriptive, which I see as taking responsibility, because the NSA is the chief cryptologic authority. It was doing its job when it was saying, like, we're the customer, you're the vendor, we need ABC, we need you to provide the resilience and so on. Part of it was they asked government agencies to inventory their cryptography to understand what needed to get fixed. I think it's often been oversimplified, I think, in many people's minds, because we went from not managing our cryptography at all, having no clue what cryptography we had, to in some cases, a super naive notion of, oh, I need to produce a list of all my cryptography, and then somehow magically it'll all get updated to quantum safe cryptography. It's a little more nuanced than that. I mean, the inventory is good, but that's kind of the bottom up approach to understanding your risk and your problem. You can still do the top down approach, right? Because any business line you have depends on cryptography, so you can actually assess your risk without an inventory. Of course, it's nice, it's good to have the inventory to kind of cross-reference, identify gaps. You have a bit of a scorecard, because over time that inventory should be less red and more green, right? You should be using algorithms that are quantum resistant. But that's really complementary to the top-down business, starting with the business lines and working down to how are they being threatened. So you should really do both of those in parallel. And again, another problem I've seen is organizations have said, well, I got to first do my crypto inventory. I don't even know how to do that before I'll do anything else. It's like, whoa, 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 that's not what the government said, right? You should do this, but they didn't say stop doing everything else. So it's a piece you can do alongside all your other activities. How do you get a crypto inventory? It's a process like going forward, we just have to manage our cryptography proactively. So it's not like we do the inventory, we migrate, and we throw it away. We have to be proactively managing and maintain that visibility on what we rely on going forward. There's a couple broad approaches for doing it. There's a few vendors, including some Canadian ones, and then close partners of Canadians who've developed, cryptographic inventory tools, really focused on this and to help with your management. Others maybe already have a lot of sensors and sophisticated tools for tracking their networks and so on. And they can either leverage what they have and maybe develop a bit more on top of that, or they can combine the two. So there's a few, I won't get in, but I mean, there's a strategy there. And we can help with that. And there's others out there who can help you strategize what's the right solution for you. How much do you build versus buy? It's really up to the end customer, but we can certainly provide guidance. There's a lot of know-how now, a lot of experience to leverage so you can come up with your strategy for your crypto inventory alongside everything else you're doing.
Okay, I think one of the questions, so we've dealt with cryptography. There's a couple of fairly technical questions in here, which I know the person asking them will probably, I'll get them to send you an email.
Sure.
Will be better. But if we talk about sort of the stack on development or the application stack on top of, our security or transport stack, a question here came up on, is this how we did things for Y2K is a little different than what this is all about, right? Yeah. There's still a date at a certain point in time. Y2K, we knew the day, but in quantum, computing, we don't know the day where this is all going to happen. But one of the questions here, I think we should just deal with, I think it's like, will we have to reprogram things? What will happen? Getting ready for cryptography is one thing, but getting ready for quantum computing might be something totally different too. So deal with both sides of that question, because there's two sides to it.
Yeah, and I'd be careful with the Y2K analogies. Just partly why I avoid the Y2Q thing is that there's some legitimate comparisons and lessons learned, and there's some really important differences. For one, the stakes were a lot lower in 2000 than they are now, and in the next 10 years. There's no adversary in Y2K. It was just the system might crash because the code has these glitches, but there's no connected adversary out to get you with all these super sophisticated cyber tools to exploit whatever they can extract. So and the fix back then was trivial, right? Just add another bit or more to the address state. It's not that sophisticated mathematics, needing the world's smartest PhDs working for over a decade to figure out how to do that. Let's add a bit, right? So the fix is much more complicated, massive interoperability challenges. Like there's a huge list as to why this is very different from Y2K. One advantage of Y2K is we had the date, and more or less, if anything was going to happen, it was going to happen then. Whereas this is not really a hard date. They'll be the first adversaries who are able to start exploiting it, and then it just gets worse and worse and worse, right? Until you've kind of neutralized the known threats, then it'll start to get better. So there's a lot of profound differences. I think many people are hung up on the lack of a date. If only I had a date. Well, you're not going to get a date, right? By the time you get a date, it's too late. So pick a date. I think that's the U.S. government did it. They're smart, but they're not smart. Everyone else is smart too. So you can pick a date, some target date, and just like they pick 6 different systems, it doesn't have to be a universal date for everything. Pick some systems with some dates, and they even, you can pretty much replicate a lot of what the governments have done in terms of picking their dates and how they staged it. I think they've shared the playbook there. I think what's missing is just leaders around the world convening at a grown-up table and picking some dates. And you need to do that sector-wise, and then the sectors need to get together as well. And so it's there is a coordination challenge there, but start within your sector, and then of course, because banking depends on telecommunications and energy, and they're all interconnected. So we have to make sure these target timelines kind of make sense. And many of them rely on the same vendors as well. So there is obviously a coordination challenge, but there's no waiting doesn't help solve this.
So I think that's something that you and I talked about just recently, is that the date being very important, the industry coming together and having a date, the sector, the global sector coming together and having a date, and then then going forward and making sure that the vendors that are supporting us are, following that, and government. So when you say preparedness, and you just mentioned the US government, I think there's many governments around the world getting prepared, not only to support their own security requirements themselves, but looking at their economies and whatever. What are you seeing? Are you seeing more activity? Are you seeing more discussion? The US was fairly vocal. How about other governments, and what are you seeing on that level globally?
So, I think the US government does deserve credit for the good work it's done, though there's different government's huge, right? So that their activities really been focused on certain parts of the government. And then in other European governments and a small set of others, they've done similar things for migrating parts of the government. But there's other massive parts of government infrastructure which I've seen very little sign of life or any reason for confidence that they're going to migrate in time, which is worrisome. So I think it'd be good to have a broader, government migration strategy, which leverages their great domestic vendors. It's a very positive upward spiral if our governments get proactive, where possible, leverage their domestic supply chains versus wait and be reactive, because there's obviously there's all the risk they're assuming by waiting, and they're also waiting. The supply chain becomes less and less trusted the longer you wait. So there's a lot of room for, I would say, more leadership from different government departments who could follow the lead of the sort of intelligence and national security elements of their governments. And some governments, like in Germany, otherwise, certain parts of the government have been actually quite proactive. Others, I find, are still in giving advice mode. That's great. Health Canada advises you to exercise and eat your vegetables. I don't know that's not enough in many cases. So yeah, in terms of government, there's lots of positive examples to follow. They just need to be followed now and go beyond just advice giving and start picking dates and start procuring from their trusted supply chain. I see more active activity on governments in terms of trying to protect their supply chains from foreign interference. Like, the biggest risk is you're not using, like, use it or lose it. But there's more of blaming the boogeyman than not that there isn't, there aren't serious threat actors out there, but there's more that's totally within our control that we could be doing there.
Okay, so that maybe I have one final question, which is, going forward, we're going to see this in the news a lot more. How do we decipher what we're hearing? Because you mentioned, sometimes a flippant comment could be interpreted one way or the other. So what's the best way from a risk community to stay apprised of what the advances are, where this going? I know that, there's a fairly high representation at the cybersecurity symposium that you hold on a biannual basis of the financial sector. But how do we decipher everything we're hearing?
It is hard. You have to figure out, like, now is a good time to figure out who you trust. And so participating in things like SIFTR and FSI-SAC and with GRI, you at least you know who to ask, and you have somebody, at least one or more people within your organization who are connected to the community and know where to look for reliable information. Some of it's just really hard because, and we get misleading information at both ends of the spectrum, right? We get this, oh, look, China's broken all our codes. And it's like, no, they didn't. Okay. So we try to quickly dispel, those kinds of things. And then you get other people saying, oh, this will never work. And it's 30 years away. So you get the nonsense at both extremes. And some it's, for a non-expert, it's really hard to tell if this recent advance out of China or anywhere really is material or not. So it's important to be plugged into a trusted community that can quickly get you a reliable answer, so you can kind of focus on the high order terms and not get distracted too much with noise.
Okay, great. Well, thank you very much, Michele. I think we were able to deal with a lot of aspects of this topic today. We've dealt with what it is, what is a quantum computer, when are we expecting them, what is it that we need to pay attention to, the dates that we're going to be paying attention to, understanding the inventory of our applications, our equipment, and then also looking at, things are being done. NIST announced their standards last year. That was a big step going forward. I think we thank you very much for all the work that Evolution Q, you, yourself, Marco Piani have done on this. One last little question is, so, this year the numbers have gone up again. Over the last 6 years, we've actually done this. We've done this report. How do you feel? Is the timeline been predicted smoothly, or are you seeing this accelerate? And maybe comment a little bit about AI and how AI has changed the landscape for quantum computing.
Yeah, sure. And I just remember I don't know if I called it out explicitly, but the Canadian Cyber Center's been tracking this for a long time. So they're a great, I would say, trustworthy resource within Canada, and their partner agents, similar in other countries as well. So yeah, I think, and partly why, a lot of people are saying, oh, we're expecting the numbers to jump like this. It's like, well, no. For one, our experts knew a lot of this stuff was going to happen, right? So a lot of this was already factored into their expectations last year, which they don't know exactly how it'll unfold over the last 12 months. So there was a noticeable uplift. Anecdotally, so again, for myself, and I know a handful of others, the fault tolerance achievements of the last year have really moved the needle in their confidence. And in some cases, you might say, well, the expected value is, the expected timeline has shrunk a little bit, but the variance has shrunk a lot too. Not to zero, so there's still uncertainty, but we're seeing the end of the tunnel a lot more clearly. So it's the mean and the variance. So the mean is, I would say, it's getting closer, but we're also more confident, and we're clear visibility in what we need to be tracking and who the players are. So in terms of the threat timeline, so I think the 5 to 10 year risk, because people will often say, oh, this is always 20 years in the future. It's like, no, it went from a 0% chance in 20 years to 10 to 80. And now we're talking about 15, and now we're talking about 5 and 10 years into the future. So the timelines, in terms of what we're focusing on and worried about, have been shrinking for very concrete, justifiable reasons as we now enter this era of quantum error correction. And I'm forgetting the last question. AI.
AI, how AI is, helping. Yeah.
So in many different ways, I mean, these are very different technologies, right? But they do interact in very meaningful ways. For one, AI and different machine learning and all these other amazing technologies can accelerate the hardware, the quantum stack, both the hardware, the software, the applications, right? So it's only going to continue to accelerate, I would say, the development of quantum computers technologically. For adversaries, it can help automate the attacking. It can help, obviously, discover new attacks, whether it's side channel attacks or code breaking attacks. But it can also automate what you can do with these new cyber weapons. Because there's many stages to launching a cyber attack. You have malware used to build a botnet, used to do denial of service, and so on. There's many different tools that come together, and this is a very when you have quantum code breaking capabilities combined with all these different aspects of AI, it's a much more powerful weapon. But let's not be afraid. Let's just prepare. Cryptography is one of the few areas where advanced computing helps the defender, but only if they use it, right? So if we architect for strong cryptography, cryptographic diversity, defense, and depth, it actually becomes harder to break the cryptographic foundations, but only if we take those initiatives. And those are the other way, and it came up in the report, is with a lot of the attention being paid to AI, which is very important. It can also sometimes limits the bandwidth we get to deal with other issues. So that's, there needs to be a balance in terms of there's your top priority, but that doesn't mean everything else gets zero attention. So there's a bit of, that observation that sometimes it's hard to get, time, mind share for this, because there's all these other opportunities and challenges we also have to deal with. But my view is this is actually much easier. Like dealing with code breaking risks is actually a much simpler problem than a lot of the risks that AI and other things can open. And we're not even dealing with these easier problems very well. So I think we can figure out how to work together on these actually somewhat easier challenges. It'll be a step in the direction of tackling some of these much harder and more opaque challenges that AI introduces.
Great. Well, thank you very much, Michele. And I'm afraid that's all the time we have for questions today. I'd like to thank Dr. Michele Mosca for joining us today to share his insights on quantum computing and its implications for our sector and for many sectors. The advancements you highlighted to us should make us pay attention to the technology and the advantages and the threats that it presents. As